Hi there. In this section, we're going to look at functions and their graphs. Specifically, we'll be looking at domain and range, how to determine if a graph itself is a function, how to determine if a relation is a function. We'll also pick up some function notation along with interval notation, and then spend the better part of the last half of this section really focusing on domain, because domain is large for this class moving forward into your trig and calculus for those of you moving forward. Math 171 is definitely not a brain dump course if you're moving on to other courses beyond this one. All right, so with that said, we'll start here with the definition of a function. A definition of a function says that each element of the domain, and your domain represents your x values, has exactly one element in the range, and the range are your y values. And in other words, an x can only match up to only one y value. Or in other words, if any of those x values repeat, a pen here. If any of those x values repeat, the relation is not a function. So there's a lot of ways that you can be asked whether something is a function or not. The first way is that you could just be given a set of ordered pairs. So I'm just going to give you a real quick set here. So if I had the set, let's say 2, 3, 2, 9, and let's say 6, 1, just a real small set here. This would not be considered a function because my x values are repeating and they're going to two different y values. So this would not be a function. But if I had this example, and let's say we had 2, 3, 1, 6, and then -5, 4, for example. This would be a function because each one of my x's are different. And so yes, that would be a function. This would both of these are referred to as a set of ordered pairs. So those curly braces indicate that it's a set, and then I've got ordered pairs inside that set. You can also be given what is referred to as a mapping, and so I'll do that. So if we had just it's kind of like two little bubbles, and you just think of this would be your x values and this would be your y values, and you can just put like a couple of x values. I'm gonna make it really easy. 1, 2, 3 over here, and then I have 5 and 9 over here. And you just draw arrows to the values. And essentially from here, at this point, if I created the ordered pairs that have been created, I have the ordered pair 1, 5, just following it from left to right, the ordered pair 2, 9, and then the ordered pair 3, 9. It's certainly okay that my y values repeat. You just always are focused on whether your x values repeat or not. All of my x values here are different, so yes, that's a function. However, if I came in and also did this and paired 1 with 9, then I add this ordered pair 1, 9, and now at that point my 1 has repeated, and so now it's not a function. Okay, so I just want to give you multiple ways to look at that. So down below then, you are going to determine if those are a function or not. So what I would recommend that you do then is pause the video, and then you can check yourself by the solution key that's posted online. Okay. All right, let's move on down then to your next term, and that is the vertical line test. The vertical line test is used to determine if a graph is a function or not. And so what the vertical line test entails is if it's possible for a single vertical line, so vertical line means up and down, to cross a graph more than one time, then it is not a function. So it's kind of like taking a pencil and dragging it across your graph. And so if if here's my pencil, so we're going to call this is A, here's B, and here's C. So think of, okay, well, here's the first time I had my pencil. Okay, I crossed the graph one time. If I do it here, I cross the graph one time. So each single vertical line is crossing at exactly one point, and as I go all the way across, each time, each of those lines is only crossing that graph one time, so yes, this is a function. Likewise, when I come over here to the next graph, if I draw my line right there, I cross here. If I draw my line right there, I just cross at one point. Every time I draw a vertical line, I only cross at one point, so yes, that's a function. Now, if we move over to part C, if you were to draw a line right there and just stop, you would say, and I meant for that line just to be tangent to that point, and so it would only be going through that one particular point. You might say, well, yeah, it's a function, but you can't just pick on one particular point. You've got to go all the way through the graph, and basically anywhere else on this graph, I'm going to go through a single line is going to go through 2 points. And so as long as if it goes through more than 1 point, then no, it is not a function. Okay, so that's the idea with the vertical line test. If you can draw a single line anywhere on that graph and it passes through more than 1 point, then no, it is not a function. Okay. All right, so let's talk about function notation. Function notation is just f of x, and it's read, as I just said it, f of x. And honestly, it's just fancy notation for a simple y equals. So down here in example 4, they want us to write these linear equations using function notation. So here, if you have y equals 5x minus 9, function notation just means, okay, well, let's replace y with f of x equals 5x minus 9. That's it, okay? It is really just, like I said, just fancy notation. A common use for it is for application type problems. So like, for example, if you were trying to figure out your monthly cost of your cell phone bill, and let's say that they charge you a base fee of $45 plus let's say 10 cents per text message, like that, then we could, of course we could do y equals, and we'd say, okay, well, y represents my cost, but it might be, more intuitive to the problem if I did it like this, C of x, that my cost is a function of the number of texts that I sent. Now, luckily for me and you and I, hopefully, or luckily for me, they don't charge me by the number of texts that I send, but that's just an example that I came up with here on the fly, okay? So, but that's a common use for that function notation, is to put it in terms of an application type problem. Okay, so that you can input, I could put input, if I've got 500 text messages, how much would it cost me that month? Or if I had just 10 text messages, how much would it cost that month? Okay. All right, so I'm going to flip it on over. Next page. At the top of the next page in example 5, it says, given this function g of x equals x squared minus x plus 7, they want us to find the following. So I've got 3 here. I'm going to work through all 3 of these. And essentially, this is just substituting. So in part A, when I say find g of 0, you can think of that g of 0 there is just above that. I'm going to think of this as g of x. So what that means is everywhere I see an x, I'm plugging in 0. So I'm going to write my problem again. That g of x equals x squared minus x plus 7. And so if I want to find g of 0, everywhere I see an x, I'm plugging in 0. So, and you'll see me throughout this semester, anytime I do any kind of substitution, I always try to use parentheses so that I keep everything straight. So anytime you take a 0 and you square it, of course you get 0, minus 0 plus 7, and so that just equals 7. So g of 0 equals 7. Now I will say this, you plugged in an x value of 0. So I want to say that you have actually created an ordered pair associated with this function. And so what this actually means then is that if you plug in 0 for x, you get a y value of 7, right? Because we said g of x is a fancy notation for y. So when we find g of 0 here, g of x, then the y value is 7. So 0, 7 is a point on that graph. Okay, but I really probably shouldn't even box that in. Technically here, your final answer is just the 7. Okay. But I just wanted to take that one step further, because that'll be something to sort of build off of as we move forward. So now moving over to letter B, if I want to find g of negative 3, again, I'm going to write my problem. So g of x equals x squared minus x plus 7. And if you like, you might want to pause the video and try g of negative 3 for yourself. Make sure you're good. But I'm going to go ahead and work it here as well. Everywhere we see an x, this time we're plugging in negative 3. So I have negative 3 squared minus negative 3 plus 7. Anytime you take a negative and you square it, it always comes out positive, because you're saying negative 3 times negative 3, so that'll give me positive 9. You'll notice here the minus sign was already there, then I replaced the x with negative 3. 2 negatives side by side become positive 3 plus 7. And now just work it from left to right. 9 plus 3 is 12. 12 plus 7 is 19. So that's your final answer. We're saying g of -3 is equal to 19. And so this time, if you want to think about, okay, what ordered pair have we created? -3, +19 is also a point on that graph, okay, of the original function here, g of x. All right, then lastly, let's step it up a notch, and let's look at the g of x minus 5. So again, I'm going to write our problem, g of x. This one says everywhere we see an x, we're going to be plugging in x minus 5. So this is going to have a little bit more work associated with it. I'm going to have x minus 5 squared minus parentheses x minus 5 plus 7. You'll see here it's super important that you use these parentheses. Now on that first one, common mistake on this is just to say, oh, this is going to be x squared plus 25. That is not legal. Anytime you have more than one term inside your parentheses being separated by an addition or subtraction sign, that means then I need to take that x minus 5, it's x minus 5 squared, so I need to take it and multiply it times itself. So x minus 5 times x minus 5. That's what that little 2 up top essentially means. Now in this next term, you have a negative in front of that parentheses, so you could think of that as a -1 that needs to be distributed to both terms. So another good reason for anytime you substitute, use parentheses. So now if I take that -1 and I distribute, -1 times x, -x, -1 times -5, +5, and then I just bring down my +7. All right, so now from here, hopefully you remember, in order to multiply x minus 5 times x minus 5, I've got to FOIL that. So foiling is multiplying your first, so x times x squared. Outside, x times -5, -5x. Inside, -5 times x, -5x. Last, -5 times -5, +25. I'm going to bring down my -x plus 5 plus 7. Okay, I'll just keep working. I'm going to go through and let's combine like terms. So I've got my x squared. And then let's combine all of our x's. So I'm going to underline here so you can see them. So I have -5x, -5x, and a -1x, imaginary 1 here. So now I need to combine all of those. They're all negative, so you add them. So 5 and 5 is 10, plus 1 is 11, but since they're all negative, I keep it, minus 11x. And then lastly, add up my numbers, underline those. I've got a +25 plus 5, that will give me 30, plus 7, plus 37. And that would be my final answer. Okay, so just so you have a little bit of practice with that. You'll want to practice some more with that and in the homework. All right, let's move on down to example 6. And it says, given the graph below, they want us to find the indicated values. So here's our graph. It's y equals 2x squared plus 4x plus 5. They want us to find f of 0. So, I mean, we could go through, since they gave us the equation here, we could plug 0 in for all of our x's and just solve. Or we could just look at the graph. When essentially this is saying when you let x equal 0, they're asking you to find the y value. So when x is 0, the y value, hopefully you agree here, is a +5. All right, the next one it's saying, okay, now let x equal -3. So when x is -3, where does that cross on the graph? Right up here, and that equals a y value of +11. Now we'll step it up a notch in the last piece. Find x, so this time you're trying to find the x value such that f of x equals 3. So remember, what does f of x stand for? F of x is just fancy notation for y. So they want to find x when your y equals 3. So let's come here. Okay, here's my y value. So when y is 3, what's the x value? A -1. So x here would equal a -1. Okay. We'll move on down then. Like I said, we're going to talk about interval notation. Interval notation will be used throughout this entire semester and moving forward. And it's used for right now, expressing solutions for inequalities and also to give you intervals for your domain and range. We'll add on to increasing and decreasing. Again, it's a technique and it's a notation that you would be using extensively again in calculus. So you want to get this down. The mathematical symbols less than and greater than always use parentheses for interval notation. Less than or equal to and greater than or equal to use hard brackets. Plus or minus infinity in interval notation will always get parentheses. You can't think about it. You couldn't cut off infinity, so that's why you can't use a bracket. It has to always be a soft parenthesis. The U-looking symbol here stands for union, and union always indicates or. I'll talk a little bit more about that as we get to problems like that. The upside down U is referred to intersection, and intersection means and, where they overlap. So I want to put that there. Again, I'll talk more about that as that arises. And then the last symbol here kind of looks like a curved E, and it is the symbol for element of. Okay. Interval notation is written using these symbols, always going from the smallest value to the greatest value. So remember, when you're referencing your domain, you're looking at your x values, and you're going to be reading your x values from left to right. For your range, you'll be reading your y values, so you'll be reading the y-axis from bottom to top, because you want to go from smallest to largest. All right, I'm going to flip it on over. At the top of the next page, they want us to write an interval notation and graph on the number line. I'm actually going to flip it. I'm going to graph it on the number line and then write the solution in interval notation. I think that'll make more sense for you. So on this first one, it says x is greater than or equal to 3. So I'm just going to draw a quick little number line here. I always put 0, and then positive 3 is just over here on the right. It doesn't have to be perfect. Okay, we just know that, okay, positive 3 is over on the right. Because it is a greater than or equal to, then that means then it's going to get a bracket. So I'm going to put a bracket here, and this inequality sign is pointing to the right, so I shade to the right. And if you think about that makes sense, because you're saying it's greater than or equal to 3. Everything to the right is greater than or equal to 3. But I will say this, as long as it's already solved for x or already solved for y when it comes to graphing on the number line, then whatever way your inequality sign is pointing, that's the way you shade. Okay, but it has to be, you have to have the letter on the left. And so now if I want to do my interval notation, okay, then I can see that my graph starts at 3 and goes on forever. So that's what we refer to as infinity. The 3, because it was greater than or equal to, got a bracket, so the 3 still gets a bracket down here, and it goes on for infinity. And like I said on the previous page, you can't cut off infinity, so infinity gets a soft parenthesis. Okay, try to be as careful as you can whenever you're doing parentheses and brackets. Brackets should be very obvious that it is a hard bracket. If you're kind of willy-nilly about what you're writing on your paper or something like that, then you could potentially lose points. If you need to commit to the bracket or commit to the parenthesis, don't make it a half, okay? Because if you make it a half, then I'm trying to guess, and I'm probably going to have to mark it wrong then. All right, let's move over to part B. This one says you've got two pieces here. X is greater than 2, so I'm going to put my 0. X is greater than 2, so we know 2's over here on the right. And since it's just greater than, I have a parenthesis, and I'm shading to the right. So it's going on forever. And then at the 0, it's less than or equal to, so I get a hard bracket, and it's less than or equal to. It's pointing to the left, so I shade to the left. And, also with that greater than or equal to, it's pointing to the right, so I shade to the right. Think of it that way. So now when I go to write my interval notation of what do I see here on this number line, I can see that the graph comes in from what is referred to as negative infinity, because it goes on forever, and stops at 0. Infinities always get parentheses. That 0 has a bracket. And then it picks back up at 2 and goes to infinity. 2 was just greater than, so it's getting a parenthesis, and infinity always gets a parenthesis. And then we use the symbol for union here, because what we're doing is we're uniting these two pieces together. Okay, so you would need to put that in your homework whenever you're doing those online. Okay. All right, so and that would be your final answer, interval notation. In letter C, it says, okay, it wants us to graph x cannot equal -4. So if I draw my number line, here's my 0, here's my -4 over here. It's just saying x can't equal that, meaning it can equal everything else but that. So what happens then is that I use parentheses because I can't equal, And I'm going to use parentheses basically going both ways. And I'm going to shade to the left because I can equal everything but -4. So I can equal everything less than -4, and I can equal everything greater than -4, like so. And so now if I were to write my interval notation here, it's coming in from -infinity to -4, parenthesis on both, unite that, picking up with -4 and going to positive infinity. So it's getting everything but that -4. If you ever have the entire number line graph, you can just simply write -infinity to positive infinity in parentheses on both. Your last one here in letter D is saying that x is between these two values. So when I go to graph my number line, I've got my 0, I've got a +5 and a -2. -2 is right beside a less than or equal to, so it gets a bracket. 5 is beside a less than, so it gets a parenthesis. And x is between these two values, so that means I shade between these two values. And so now when I go to write my interval notation, I start at -2 and go to 5. -2 has the bracket, 5 has the parenthesis. Final answer. Okay. Let's move on down to example 8. If at any time, I'm going to probably do throughout this entire set of notes, but if at any time you want to ever pause it so you can try one on your own, feel free, okay? So looking down here, example 8, find the domain of the domain graphically. A couple of these first couple you should know without having to put in your calculator, but if not, you can certainly put it into y equals and graph it. But hopefully you recognize, oh, well, this first one, f of x, okay, this is y equals x plus 1. This is just a linear line, right? It's got a y-intercept. We'll talk a little bit more about this in the next section, but it's got a y-intercept up here of 1 and a slope of up 1 over 1. So it kind of looks like this. Like again, I'll hit that harder in the next section, but that's what you would see in terms of a graph here. It wants the domain. So the domain is you're reading this graph from left to right. So think about it. This graph is going down and to the left forever, so it's going to the left forever, and it's going up and to the right forever, so it's also going to the right forever. So my domain here, then, we can simply say is going from -infinity to positive infinity. It's perfectly fine for you to do that, and I believe that's what you have to do when you're online. But if you ever needed to, another way that you could say this is that the domain here would also be all real numbers, and that's the symbol for all real numbers. Is I can write it again for you so I can say it. It's like 2 vertical bars, and then you just make an R like so. And that means all real numbers is the symbol for all real numbers. Move on over to letter B. If I were to crank out this graph and try to figure out what its domain is, domain, remember, reading your x-axis from left to right. This is x squared, means a parabola. This +2 just shifts me up 2 units. So it roughly looks something like this. Again, you can put this into y equals. Y equals x squared plus 2 and hit graph in your calculator. Zoom 6 in your calculator gets you a nice viewing window. And this would be what you would see. And so again, think about this graph in terms of left to right. It's going up and to the left, up and to the right. So it's going left and right forever. So therefore, again, -infinity to positive infinity for our domain, or we could just simply, as again, say all real numbers. Letter C, a cubic function. I'm just going to crank out a little general graph here. Looks something like this. It's not perfect or to scale, but it's something like that. Again, thinking about reading this from left to right, I know it's going down, but as it goes down, it goes left. As it goes up, it goes right. So it's going left and right forever. So again, -infinity to positive infinity, or all real numbers for your domain. All right, and the last two is going to take a little bit of, it's going to look a little differently. So in letter D, if you don't know what that one looks like, if you were to take it and put it into y equals, you would see over here at -3, the calculator probably doesn't show you this asymptote line, and that's okay that it doesn't. But you should be able to sort of tell in your calculator that it is kind of approaching a particular point and not touching it, and that's referred to as an asymptote. So what we would say, okay, in terms of our graph here, reading our domain, reading it from left to right, it's coming in from -infinity, and it gets really, really close to -3, but it never actually equals -3. So it comes in from -infinity to -3. And then it picks back up here in this top quadrant and goes from -3 and then goes to the right forever to positive infinity. And then we just put our little u here in the center. So it goes from negative infinity to -3 and then -3 to positive infinity. Let me ask you this. How does that -3 that I've drawn here on the graph as part of the domain, how does the -3 relate to h of x? Your given function up here. How does a -3 relate to that function? Hopefully you recognize that -3, if you were to plug it into the denominator, it makes your denominator equal 0. It makes your denominator equal to 0. And that's a bad thing, right? Because if your denominator equals 0, then you're undefined at that particular point. So this will be a new rule, and I have it on the next page for you, but I'm going to go ahead and explain it here in real time. What happens then is you exclude values that make the denominator equal to 0 from the domain. Exclude values that make the denominator equal to 0 from the domain, because if it's making the denominator equal to 0, then it's making the function undefined. Okay? All right, let's look at letter E here. In letter E, if you were to graph this function, you would see that over here at -4, 2, 3, 4, so here's my -4, a point, and I'm just going to roughly look something like this. So if we were to identify our domain for this particular problem, we would say, okay, well, the leftmost point it starts at is -4, and then it goes to the right forever, so that would be infinity. The -4 is a point on the graph, right? So I put a bracket there. Infinity always gets a parenthesis. So that would be my domain. Again, on all these problems, we've been identifying what our domain is. And now I'll ask you this. How does -4 relate to this function, f of x? Look back at our function here. How does that -4 relate to that function? Hopefully you would agree that in this case, it makes the square root equal to 0. And it's okay that it equals 0, but in terms of a domain, you'll always need to make sure that all even roots must be set greater than or equal to 0 in order to solve for the domain. And so essentially here, if we go back and look at it, okay, if I have x plus 4 is greater than or equal to 0, if I solve for x, I just subtract 4 from both sides. X is greater than or equal to -4. If you think about that on a number line, here's your 0, here's your -4, greater than or equal to says give me a bracket, and it's point to the right, so I shade to the right. And so sure enough, algebraically here, this is giving me the domain. Up here, this is what our graph generated. They both coincide. It will always be that case. I don't want to gloss over this fact. You're only concerned about even roots, because what happens is we can't take an even root of a negative number. You can't take the square root of -4. You can't take the square root of -16. Technically we can. They're called imaginary numbers. We'll get there later in this semester, but for right now, as we talk about domain, even roots, okay, so I mean, I'm talking about the square root, the fourth root, the sixth root. Even roots, when you find the domain, you're always setting greater than or equal to 0. Now, if it was a cube root up here, it would just be all real numbers, okay? Because think about it, you can take the cube root of a negative number. So if you had the cube root of -8, that's -2. Right? Because what that means then is -2 times -2 times -2, that equals -8. But the square root of -8 is not real. Okay, it's imaginary. That's coming later. the unit 3. Okay, so something to look forward to. All right, so let's flip it on over. Top of the next page, I kind of summarized those pieces that I was just talking about. So they're really referred to as domain restrictions. When you have a variable in the denominator of your function, you're going to set that denominator equal to 0 and solve for x. These are values, get our highlighter here. These are values that are excluded from your domain. X cannot equal those particular values, okay? When you have an even root in your function, you're going to set the argument underneath the radical. So that means then the piece underneath the square root, so the argument underneath that radical greater than or equal to 0 and solve for x. That will be your domain, okay? It's not something you exclude. That actually will be your domain. Another key piece here is that if the radical is in the denominator, you simply set it greater than 0, not greater than or equal to, okay? Because if it's in the denominator, think about it, it can't equal 0, because if it equals 0 in the denominator, then it's undefined. Of course, I've got an example down here for you, but I want to point it out to you and highlight it for you. You're still solving for x. All right, so let's look here at example 9. So essentially, if you don't have one of these pieces here where if you don't have something at a denominator and you don't have an even root, then your domain doesn't have any restrictions, and you can just say, oh, well, my domain's all real numbers. So let's kind of point that out to you. So if we're looking at here in example 9, part A, they say find the domain without a calculator and then verify with a graph. So g of x here, it says absolute value of x plus 4. Well, like I just said, it doesn't have a square root in it. It doesn't have a denominator. So the domain should be negative infinity to positive infinity, right? Sure enough, if you were to graph this function, absolute value functions are always your V-shaped curves. You would find that it's over here, negative 1, 2, 3, 4. This is negative 4. It would look something like this. This is not a perfect graph, but you get the idea. Would look something like that. This graph is going up and to the left and up and to the right forever. So it's going left and right forever. Negative infinity to positive infinity for my domain. Okay. Letter B. I've got a square root, right? What my rule up there said is if set what's underneath the square root, underneath the radical, this argument here, 7 minus x, greater than or equal to 0, and solve for x. So subtract 7. Negative x has to be greater than or equal to negative 7. Think of this as a negative 1. Can't leave that, so you divide both sides by negative 1. The rule is anytime you multiply or divide by a negative, you have to change that inequality sign. So notice here I'm going to change that to now less than or equal to. And then negative 7 divided by negative 1 is a positive 7. So now if we think about our interval notation for this, okay, so I've got, here's my 0, here's my positive 7. It would have a bracket, and it's pointing to the left, so I'm going to shade to the left. So if I were going to do domain from what I see here, then I would say, okay, well, it's coming in from negative infinity and stops at 7. Infinity always gets a parenthesis, and that 7 would have a bracket. That would be your domain. That would be your final answer. If you now go and check yourself in a calculator, you would find over here at positive 7, it touched down there, and then it kind of comes back over here to the left forever. So again, if you read this graph from left to right, it's coming in, it's going to the left forever, it's coming in from negative infinity, and then it stops at 7. You're just reading your x-axis. All right. Letter C, I've got a denominator. Denominator, it cannot equal 0. So as the top of the page here says, if you've got a denominator, set it equal to 0. Essentially, you're saying x minus 3 cannot equal 0. That's probably the best way to do it. X minus 3 cannot equal 0. Solve for x. Add 3 on both sides. So x cannot equal positive 3, meaning my domain can equal anything but positive 3. So that would be negative infinity to positive 3. And you then unite that with 3 to infinity. It can equal anything but that. So remember back on the previous page when we did on the number line, here's my positive 3. It can go to the left forever, and it can go to the right forever, but it cannot equal that 3. So that's my interval notation. if you were to put this in your calculator and graph y equals x plus 5 over x minus 3, you would need to be sure in your y equals that you put the top in parentheses divided by the bottom in parentheses. I recommend that, if you were in class right now, I would be pausing and telling you, okay, put this in your calculator. So pause the video, take the time, put it in your calculator so you can make sure that you're able to generate this graph. So kind of looks at 1, 2, 3. Again, you're not going to see this little dashed line that I'm drawing. I'm kind of doing it for myself as a guideline. And graph looks something like this. But you can tell that what ends up happening with this asymptote, it kind of comes in and it hugs that asymptote. So it's coming in from negative infinity, stops at 3, picks back up here in the top quadrant at positive 3, and goes to the right forever. So positive infinity. All right, so then let's look at letter D. Letter D is the one that I was referring to up here at the top of the page, where I said, if you have a radical in the denominator, meaning you've got a square root in the denominator, simply set it greater than 0. Okay, so at this point, instead of setting x plus 6 greater than or equal to 0, I just set it greater than 0 because it's in the denominator, it can't equal 0. If it equaled 0, it would make it undefined. Solve for x, so subtract 6. X has to be greater than negative 6. You might, at this point, you might be getting better and you don't need to use the little number line here. I'm going to continue to show it just for a little while longer. So here's my negative 6. It is just a greater than, so I'm going to get a parenthesis, and it's pointing to the right, so I'm going to shade to the right. And so now if I do my interval notation for my domain, I can see that my graph starts at negative 6 and goes to the right to infinity forever, and parenthesis on both. That would be my domain. Take the time, put it in your calculator. You should see that it looks something like this over here at negative 6. Kind of looks like that. It's kind of like there's an asymptote. There really, well, it's not even kind of. There's an asymptote there. Like so. Okay, so from negative 6 to infinity. And now moving on down to example 10. So it wants us to find the domain and range of this particular function. So just adding one extra piece, adding the range to it. So you have a square root. So again, that square root has to stay positive. And it could equal 0 because it's not in the denominator. So we set x plus 4 greater than or equal to 0. Subtract 4 from both sides. X is greater than or equal to negative 4. So then I can say, if I look at my graph, I've got my negative 4. It's greater than or equal to, so it's getting a bracket. It's pointing to the right, so a shade to the right. So I can identify my domain then as being from negative 4 to infinity. And notice how with the negative 4 I put a bracket. It's going to the right forever, so infinity, and it always gets a parenthesis. So there's my domain. Let's look at the graph. So if you were to pop that in your calculator, you would see that negative 1, 2, 3, 4. So it's negative 4, negative 5. This is negative 5. There would be a starting point on your graph down here at negative 4, negative 5. And then it kind of looks like it just comes up and goes like so. So now if I read my range, so if domain is reading your x-axis from left to right, range is now reading your y-axis from bottom to top. So my smallest y value is down here, and that y value corresponds to negative 5. And then it goes up forever. I mean, it's not going up sharply, but it's going up and to the right incrementally. So it would go from negative 5 to infinity. That negative 5 is a hard point down there, so it gets a bracket. Infinities always get parentheses. So that would be our domain and range. I'm just going to add a little example over here to the side for you. So if I were to graph this for you, let's say we had, I just want to make up something kind of like, so you have it. And let's just say that I'm just saying this point down here is the point negative 3, negative 5. And this point up here is the point 2, 8. And now if I ask for my domain and my range. Domain, I'm reading my x-axis, so smallest x value. So here's your smallest x value, and I'm saying, okay, well that smallest x value then is -3, and then to your largest, most rightmost x value, okay, that's +2. Notice down here at -3 that it's an open circle. That open circle indicates a parenthesis. Up here at the 2 is a closed circle, so that indicates a bracket. For my range, smallest y value down here at -5, and then goes up to largest y value up there at a +8. Same thing. This -5 has an open circle, so it gets a parenthesis. The +8 has a closed circle, so it gets a bracket. Okay, so just another little example there to express that for you. Okay, all right, let me know if you need anything. Thanks a lot. Bye.